Welcome back to QubitInk. In the previous video, we built the basic postulates of quantum mechanics using state vectors. That language is elegant, and for a perfectly known pure state, it works beautifully. But now we are going to ask a slightly more realistic question. What if we do not know exactly which quantum state was prepared? Well, imagine a source that sometimes prepares one state and sometimes prepares another. Each individual state still follows the usual rules of quantum mechanics. But now there is an additional layer of uncertainty coming from the preparation itself. So we have quantum uncertainty, and on top of that, ordinary statistical uncertainty. This is where the density operator becomes the natural language. Instead of describing the system by one state vector, we describe an ensemble of possible states together with their preparation probabilities. Mathematically, those possibilities are combined into a single operator, conventionally written as ρ. Let us look at this from another angle. A pure state can also be represented by a density operator. So we are not throwing away the state vector description. We are embedding it inside a more general framework. And that extra generality becomes extremely useful. With density operators, unitary evolution has a compact operator form. Measurement probabilities can be written using traces. Pure and mixed states can be distinguished mathematically. And when a larger quantum system is entangled, the state of one subsystem is described naturally by a reduced density operator. That last point is especially interesting. A 2-qubit system can be in a completely known pure state, while either qubit, considered by itself, can look maximally mixed. It sounds strange at first, but the mathematics will make the reason very clear. So, in this video, we will develop the density operator formalism in 3 stages. First, ensembles of quantum states. Second, the general properties of density operators, including positivity, trace, eigenvalues, and purity. And third, the reduced density operator and the partial trace. By the end, we will have a description of quantum states that is powerful enough for uncertainty, entanglement, subsystems, and much of quantum information theory. Alright. Let us begin with the central idea, an ensemble of quantum states. Suppose we have a preparation device. Each time we press the button, it produces a quantum system. But the device does not always prepare the same state. Perhaps it prepares one state with probability P1, another with probability P2, and so on. We describe this collection by pairing every possible pure state with the probability that it was prepared. This is what we mean by an ensemble of pure states. Now, there is an important point here. The probability attached to a state is not a measurement probability inside that state. It describes our uncertainty about the preparation itself. Once a particular state has been prepared, that state may of course have its own quantum measurement probabilities. So these are 2 logically different layers of probability. Well, how do we package the whole ensemble into one mathematical object? For each possible state, form the projector associated with that state. Then weight that projector by the corresponding preparation probability, and add all the contributions. The resulting operator is the density operator, usually written as ρ. This is the defining equation for an ensemble. Notice what has happened. The individual state vectors have not disappeared. Each one contributes through its projector. But the classical probabilities of the preparation procedure are now built into the operator itself. Let us make this concrete with a qubit. Imagine that the source prepares the 0 state half of the time and the 1 state half of the time. The density operator is then 1/2 times the projector onto 0, plus 1/2 times the projector onto 1. In the computational basis, that becomes a 2x2 matrix with 1/2 on each diagonal entry and 0 off the diagonal. In other words, it is 1/2 times the identity matrix. This state is called the maximally mixed state of a qubit. Now compare that with a very different preparation. Suppose every qubit is prepared in the plus state, an equal coherent superposition of 0 and 1. The measurement probabilities in the computational basis are again 50-50. So if we only measured 0 versus 1, the 2 preparations might look the same. But their density matrices are not the same. For the plus state, the density matrix contains off-diagonal terms. Those terms encode coherence between the basis states. For the 50-50 classical mixture of 0 and 1, the off-diagonal terms vanish. This is a distinction worth remembering. A coherent superposition is a pure quantum state. A statistical mixture represents uncertainty over different preparations. Equal measurement probabilities in one basis do not make those 2 situations equivalent. The density operator keeps track of that distinction. Now let us see whether the familiar rules of quantum mechanics survive in this language. Start with unitary evolution. Suppose the closed system evolves under some unitary operator U. If the preparation happened to produce state psi sub I, then ordinary state vector quantum mechanics tells us that the state becomes U acting on psi sub I. The probability p sub I does not change merely because we apply the same unitary evolution to the system. So every projector in the ensemble transforms in the corresponding way. When we collect the terms again, the whole density operator evolves very simply, rho becomes U rho U dagger. This is the density operator version of unitary evolution. It is exactly equivalent to the state vector rule. The advantage is that the same formula works whether rho describes a pure state or a mixture. Now let us turn to measurement. Suppose a measurement is described by operators m sub m, where m labels the possible outcomes. If we knew that the initial state was psi sub I, then the probability of outcome m would be given by the usual measurement rule. But in an ensemble we do not know which preparation occurred. So let us reason carefully. For each possible initial state, there is a conditional probability of obtaining outcome m, given that state. Then we weight that conditional probability by the chance that the state was prepared. Finally, we sum over all possible preparations. That is simply the law of total probability. And this is where the trace becomes beautifully useful. Each conditional probability can be rewritten as the trace of the measurement operator combination multiplied by the corresponding projector. Once we sum over the ensemble, all those weighted projectors combine into rho. The final result is compact. The probability of outcome m is the trace of m dagger m times rho, with the appropriate measurement operator carrying the label m. So the familiar Born rule has not changed. We have simply rewritten it in a form that works directly with density operators. Let us stop for a moment and interpret that. The density operator contains exactly the information needed to predict measurement statistics. If two different preparation procedures give the same density operator, then no measurement performed only on that system can distinguish those preparations by their outcome statistics. That observation will become very important later. But measurement does more than produce probabilities. It also changes the state. So what happens to the density operator after we obtain a particular result m? Again, start with one possible member of the ensemble. If the initial state was psi sub I and outcome m occurred, the state vector measurement postulate tells us how to update that state, apply the measurement operator and then normalize. But after seeing the result m, our classical knowledge about the preparation also changes. Some initial states may have been more likely than others to produce this result. So the probabilities for the members of the ensemble must be updated as well. This is an ordinary Bayesian update sitting inside a quantum measurement problem. The new probability that the preparation was I, conditioned on observing m, is proportional to two things: how likely preparation I was before the measurement, and how likely outcome m was if preparation I had occurred. When we combine that classical update with the quantum state update and simplify, something very clean emerges. The post-measurement density operator is obtained by placing rho between the measurement operator and its adjoint, and then dividing by the probability of the observed outcome. So, conditioned on result m, the updated state is m sub m, rho, m sub m dagger, divided by the trace that gives the probability of m. This formula is one of the main reasons the density operator language is so useful. It combines the quantum update and the classical update into a single expression. Well, let us push the idea one step further. What if the measurement happened, but we did not learn which result occurred? Maybe the apparatus recorded the result and the file was lost. Or perhaps the result was deliberately ignored. For each possible measurement result m, there is a corresponding post-measurement state, and that state occurs with probability p of m. If we average over all those possibilities, the probabilities and normalization factors cancel in a very convenient way. The resulting state is the sum over all outcomes of m sub m rho m sub m dagger. This is no longer a conditional state. It is the state when the measurement outcome is unknown. Notice the physical meaning. When the record of the measurement result is available, we condition on that result and use the normalized post-measurement state. When the result is unavailable, we must keep all possible branches and mix them according to their probabilities. The difference is information. The underlying physical interaction may be the same, but what we know about the outcome changes the state assignment we should use for future predictions. Now we can introduce the terminology more carefully. If the quantum state is known exactly as a single state vector, we call it a pure state. Its density operator is simply the projector onto that state. If the density operator represents a non-trivial statistical mixture of possible pure state preparations, we call it a mixed state. A useful diagnostic is based on squaring rho and taking the trace. For a pure state, the trace of rho squared is 1. For a genuinely mixed state, it is less than 1. We will study this criterion more systematically when we examine the general properties of density operators. For now, it gives us a convenient preview of the distinction. There is one more useful extension. Suppose the preparation procedure does not choose directly between pure states. Instead, it chooses between density operators ρ1, ρ2, and so on, with corresponding probabilities. The same logic still works. The overall density operator is simply the probability-weighted sum of those density operators. So mixtures can be nested. An ensemble of mixed states is described by the mixture of their density matrices, just as an ensemble of pure states is described by the weighted sum of their projectors. This becomes especially useful when we study noise, because noise often creates uncertainty about what transformation or disturbance actually occurred. Let us collect the main structure. An ensemble is a set of possible quantum states together with preparation probabilities. Its density operator is the probability-weighted sum of the corresponding projectors. Closed system evolution acts by sandwiching rho between U and U dagger. Measurement probabilities are obtained from a trace. Conditioned on a known measurement result, the state is updated and normalized using that result. If the result is forgotten, we average over the possible measurement branches. And pure states appear as a special case of the same formalism. So the density operator is not a different theory of quantum mechanics. It is the same quantum mechanics reorganized into a language that can handle both quantum amplitudes and classical uncertainty without switching formalisms. In the next part, we will stop referring to a particular ensemble and ask a deeper mathematical question. Given an operator ρ, how can we tell whether it is a valid density operator at all? That takes us to the general properties of the density operator. We now know how to construct a density operator from an ensemble of quantum states. But let us reverse the question. Suppose someone simply hands us an operator, ρ. How can we decide whether it is a physically valid quantum state? The nice result is that we do not need to know how the state was prepared. We can characterize a density operator directly from the operator itself. There are two conditions. First, ρ must have trace equal to 1. Second, ρ must be a positive operator. That is the complete characterization. Well, let us understand why these conditions appear. Start with the trace condition. If ρ comes from an ensemble, then it is a probability-weighted sum of projectors onto normalized states. The trace of each such projector is 1. So when we take the trace of ρ, we simply add the preparation probabilities. And because those probabilities sum to 1, the trace of ρ must also be 1. So the trace condition is really the normalization of probability written in operator language. Now let us look at positivity. Take any vector phi in the state space and place ρ between the corresponding bra and ket. If ρ was constructed from an ensemble, the result becomes a sum of terms. Each term is a non-negative probability multiplied by the absolute square of an inner product. Every contribution is non-negative. Therefore the expectation value of ρ in any vector must be greater than or equal to 0. That is exactly what it means for ρ to be a positive operator. So far, we have shown that every density operator must satisfy trace 1 and positivity. But the more interesting direction is the converse. Suppose we start with an operator that is positive and has trace 1. Is that automatically a legitimate density operator? Yes. Because a positive operator is Hermitian, it has a spectral decomposition. So we can write ρ as a sum over orthogonal eigenvectors, with the corresponding eigenvalues in front of their projectors. Positivity tells us that every eigenvalue is non-negative. The trace condition tells us that those eigenvalues sum to 1. And now something rather elegant happens. Those eigenvalues can be interpreted as probabilities. The spectral decomposition therefore has exactly the form of an ensemble. Prepare eigenstate j with probability lambda j. So any positive operator with trace 1 can arise as the density operator of some ensemble. This gives us the intrinsic definition we wanted. A density operator is a positive operator with unit trace. Let us pause here, because this statement is more powerful than it first appears. We no longer need to begin quantum mechanics by saying that the fundamental state must always be a state vector. We can formulate the theory directly using density operators. The state of a system is represented by a positive, trace 1 operator. Closed system evolution still takes ρ to u ρ u dagger. Measurement probabilities are still calculated using the trace rule. And after a measurement outcome is known, the state is updated by the normalized measurement transformation we derived in the previous section. For composite systems, independently prepared states combine by the tensor product. So the four postulates we developed earlier can be rewritten entirely in density operator language. The mathematics is equivalent, but the language is now broad enough to include both pure and mixed states from the start. Now let us examine the eigenvalues a little more closely. Since ρ is positive, all of its eigenvalues are non-negative. And because their sum is 1, every eigenvalue lies between 0 and 1. So the spectrum of a density operator looks like a classical probability distribution. For a pure state, the situation is extreme. There is one eigenvalue equal to 1 and all the others are 0. For a mixed state, probability weight is spread across more than one eigenvector. This leads naturally to a useful quantity called the purity. We calculate it by squaring ρ and taking the trace. Using the spectral decomposition, squaring ρ simply squares each eigenvalue. So the purity is the sum of the squared eigenvalues. Now remember that the eigenvalues are non-negative and sum to 1. The largest possible value of that sum of squares is 1. And equality occurs only when all the weight sits on a single eigenvalue. Therefore every density operator satisfies purity less than or equal to 1. A pure state has purity exactly 1. A mixed state has purity strictly less than 1. For a qubit, the maximally mixed state gives purity 1/2. So purity gives us a compact numerical test for how mixed the state is, although later we will meet more refined measures. At this point, there is a subtle issue that is easy to miss. Because ρ has a spectral decomposition that looks like an ensemble, it is tempting to think that its eigenvectors and eigenvalues tell us which states were actually prepared and with what probabilities. In general, they do not. The spectral decomposition gives one possible ensemble representation of ρ. It is not necessarily the physical preparation history. Let us see an example. Consider a qubit density operator with probability 3/4 on 0 and 1/4 on 1. That certainly can arise by preparing 0 3/4 of the time and 1 1/4 of the time. But it can also arise from a different ensemble. Take two non-orthogonal states, one with a positive superposition component and one with a corresponding negative component, and prepare each with probability 1/2. When their projectors are averaged, the off-diagonal terms cancel. The result is exactly the same density matrix. So two genuinely different preparation procedures can lead to the same ρ. And if the density operators are identical, then no measurement performed only on that system can tell which ensemble was used. This is an important conceptual shift. The density operator is the physical state description available for predicting measurements. A particular ensemble decomposition is one way of realizing that state, but generally not a unique one. Nielsen and Chuang make this precise using what they call unitary freedom in the ensemble. Very roughly, if two ensembles generate the same density operator, their probability-weighted state vectors are related by a unitary mixing of the ensemble labels, after padding with 0 probability entries if necessary. We will display the precise relation on screen, but the main message is simpler. The same density matrix can have many ensemble decompositions. So we should not confuse the spectrum of ρ with a unique preparation story. Let us collect the main results. A valid density operator is positive and has trace 1. Positivity guarantees non-negative eigenvalues. Unit trace makes those eigenvalues sum to 1. The spectral decomposition proves that these two conditions are also sufficient. Pure states have one eigenvalue equal to 1 and purity equal to 1. Mixed states distribute weight across several eigenvalues and have purity below 1. And finally, a density operator does not in general determine a unique ensemble of pure states. That gives us a complete intrinsic picture of ρ. In the next section, we will see where this formalism becomes especially powerful. We will take a composite quantum state and ask, what is the state of only one part of the system? The answer is the reduced density operator, obtained using the partial trace. We now come to one of the most important uses of the density operator, describing only part of a larger quantum system. Suppose systems A and B together are described by a joint density operator. Now imagine that we have access only to system A. What is the state of A alone? Well, we cannot simply erase the symbols that belong to B. Quantum correlations between the two systems may be present, and whatever state we assign to A must still reproduce every measurement that can actually be performed on A. The object that does this is the reduced density operator. For system A, we define it by taking the partial trace over system B. So the reduced state of A is obtained from the joint state by tracing out B. At first this can look like a formal prescription. So let us slow down and understand exactly what the partial trace does. Consider a simple operator that is a tensor product of an operator on A and an operator on B. For the A part, the partial trace does nothing. For the B part, it takes the ordinary trace. In the special case built from outer products, the B factor therefore reduces to an inner product. So the part belonging to A remains as an operator, while the part belonging to B collapses to a scalar. And because the partial trace is linear, this rule extends term by term to any operator on the composite system. That linearity is what will make the Bell state calculation particularly clean. But now comes the more important question. Why should this mathematical operation represent the physical state of a subsystem? This deserves a real answer. Suppose M is an observable that we want to measure on system A. If we describe the same physical measurement while keeping the full system AB in our mathematics, then the observable must act as M on A and as the identity on B. We are measuring A. We are doing nothing to B. So, on the composite Hilbert space, the corresponding observable is M tensor the identity on B. Now physical consistency demands something very simple. The average value predicted for that measurement must be the same whether we calculate it using the reduced state of A, or using the full state of A and B. Using the reduced description, the average is the trace of M times rho A. Using the full description, the average is the trace of M tensor identity times rho AB. Those two numbers must agree for every observable M acting on A. And this is exactly what the partial trace guarantees. This is the real reason we use it. We are not tracing out B because it is a convenient trick for deleting variables. We are tracing out B because the resulting operator contains precisely the information needed to predict every measurement that can be performed locally on A. In fact, Nielsen and Chuang make an even stronger statement. Among maps from the joint density operator to a density operator on A, the partial trace is uniquely fixed by this requirement that all local expectation values come out correctly. One way to see the uniqueness is to expand an arbitrary candidate reduced state in an orthonormal basis of Hermitian operators on A. The coefficients of that expansion are its inner products with the basis operators. But those coefficients are exactly the expectation values that the consistency condition already fixes from the full state. So once every observable on A has the correct expectation value, there is no freedom left in the reduced density operator. That is a beautiful point. The partial trace is not merely one reasonable choice. It is the unique state assignment compatible with all observables available to the subsystem. Let us check the definition on the simplest case. Suppose the joint state is a product state, rho tensor sigma. There are no correlations here. A is described by rho, and B is described by sigma. Now trace out B. The rho factor is left untouched, while sigma contributes its trace. But sigma is itself a density operator, so its trace is 1. What remains is exactly rho. That is precisely what we would expect. If two systems were prepared independently, ignoring B should not mysteriously change the state of A. Alright. Now let us move to the example where the reduced density operator becomes genuinely interesting. Take the Bell state formed from 0, 0 and 1, 1 with equal amplitude. The joint state is pure and completely known. First construct its density operator by multiplying the state by its corresponding bra. When we expand that outer product, 4 terms appear. There is a 0, 0 diagonal term. There is a 1, 1 diagonal term. And there are 2 cross terms connecting 0, 0 with 1, 1. Now we trace out the second qubit. Because the partial trace is linear, we can work through these 4 terms one at a time. Start with the 0, 0 diagonal term. Tracing over the second qubit produces the overlap of 0 with 0. That overlap is 1. So the first term survives and leaves the projector onto 0 for the first qubit. Now look at the term that connects 1, 1 with 0, 0. Tracing over the second qubit produces the overlap of 0 with 1. Those basis states are orthogonal, so the overlap is 0. Therefore that entire cross term disappears. The other cross term disappears for exactly the same reason, it contains the overlap of 1 with 0. And finally, the 1, 1 diagonal term contains the overlap of 1 with 1. That equals 1, so the projector onto 1 survives. So after tracing out the second qubit, only 2 terms remain. We obtain 1/2 times the projector onto 0, plus 1/2 times the projector onto 1. And in matrix form, that is simply 1/2 times the identity. So the reduced density operator of the first qubit is I/2. This is a remarkable result, and it is worth thinking about carefully. The state of the two-qubit system is pure. We know the joint Bell state exactly. Yet the first qubit by itself is maximally mixed. Its purity is 1/2, strictly below 1. Exactly the same is true for the second qubit. So complete knowledge of the whole does not imply complete knowledge of each part. In fact, for this entangled state, the information is stored in the correlations between the two qubits rather than in either qubit considered separately. Locally, each qubit looks completely random. Globally, the pair has a perfectly definite quantum state. That contrast is one of the characteristic signatures of entanglement. And now the purpose of the reduced density operator should be much clearer. When we focus on one subsystem, we do not try to invent a state vector for it. We trace out the degrees of freedom we are not describing. The result is the unique density operator that reproduces all local measurement statistics. For an uncorrelated product state, this simply returns the original local state. For an entangled state, the reduced state can be mixed even though the joint state is pure. That is precisely why the density operator formalism is indispensable for composite quantum systems. We have now reached the central result of this section. A pure Bell pair can give a maximally mixed state for either individual qubit. In symbols, the joint state is perfectly pure, while the reduced state is I/2. We will stop here and let that result settle. In the short closing section, we will summarize what the density operator formalism has given us and look ahead to the next tools for understanding entanglement. That brings us to the end of our introduction to the density operator. Today we saw how ensembles lead naturally to the density matrix, how its general properties characterize valid quantum states, and how the reduced density operator lets us describe subsystems through the partial trace. Most importantly, we saw a central lesson of composite quantum systems. The whole system can be in a pure state even when each subsystem is mixed. For the Bell state, the reduced state of either qubit becomes I/2. In the next video, we will take the natural next step from the book and study the Schmidt decomposition, together with its connection to purifications. After that, we move toward the EPR paradox and the Bell inequality, where the structure and meaning of entanglement become even sharper. If you enjoyed this video, you can also follow QubitInk on Instagram. And if you have questions, suggestions, or ideas for future topics, feel free to reach out by email. Thank you for watching. Keep exploring carefully, keep asking good questions, and I will see you in the next video.